So, thank you all very much for coming, for giving up your afternoon and your evening to come and support this. Hopefully, I'm looking forward to a really, really good evening. The speeches promise to be very interesting. Some very, very technical topics I'm looking forward to learning more about from our speakers who will introduce themselves at the time as they come up. I'll hand over to our judging panel shortly so they can introduce themselves, but on behalf of the RAeS Society and from the local branch, thank you all very much for coming, and thanks to our speakers for giving up their time to come and talk to us. So hope you all have a good evening. Hand over to the judges now. Well, you just need to talk in this one.
Okay, so I'm Paul Minion from the MBDA. I'm the Test and Evaluation Advisor within the engineering organisation in the UK. My background is in test proving aircraft integration, going back with at least 40 years now. So that's me.
Good evening, everyone. My name is Ian McCall. I'm the VP for Engineering for Future Combat Air at Leonardo in Luton. My background for many years was radar design and development. So I've been involved in all stages of the life cycle in developing radars, from mathematical modelling all the way through to kind of trials and verification activities. And this is the first time that I've attended tonight. So very much looking forward to hearing the presentations and learning more about some new topics. So thank you very much for the invitation and over.
Good evening, everyone. My name is Sam Leather. I'm part of the staff team at the Royal Aeronautical Society, our office in London. I work in the Society's community engagement team, and I'm the main point person for admin support to the Society's branch network. Aside from that, I have a background in aviation history. I have an undergraduate degree in war studies, first class from the University of Birmingham, and a master's degree with distinction in the history of warfare, also from the same institution.
I think therefore we invite our first speaker up. And, mouse counting this is a clicker if you'd like. If you want to say from the phone. I mean, you back the cards. I will be at the back holding the cards. There's a microphone, please.
Right, does that work? Good. Right. Started off then. So, good afternoon, everybody. My name is Oliver Tatlow, and I'm going to be presenting a bit of a history of stealth. The first thing that I would like to talk about, if this changes, is surprise. The joke there is for me to shout that, but I'm not going to do that. So, the SAS Commando RAeS in World War II inflicted massive damage with minimal losses, despite being deep behind enemy lines. How did they do this? Surprise! They went in behind enemy lines, undetected, and inflicted these wrecks. Now, if the enemy had known that they were there, the losses would have been substantial, but they weren't. Surprise in this case acted as a force multiplier. But we saw this on the ground. Why didn't we see it in the air during the war? And the answer to that is radar. Now, chain home, seen here, enabled the smaller RAF to beat the Luftwaffe in the Battle of Britain. It did that because it gave us time to prepare and defend ourselves. Now imagine the power of the SAS and destructiveness in the air, airborne behind enemy lines. That is powerful. And much as the Russian Chief of the General Staff said in 1984, stealth, which is what it is, can make conventional attacks just as effective as nuclear. So how does stealth work? Well, we're going to start off, for anyone who doesn't know how a radar works. You send a beam of electromagnetic energy, it then bounces off of something, and you receive what comes back. You know how far away it is based on how long it's taken, and you know the direction based on the direction that you fired that wave in the first place. But we'll start with stealth. And in physical stuff here, you have shaping. So if you imagine looking at a mirror face on, you can see the reflection because the light comes off of your face, it bounces off the mirror, and you see it again. But if you stand at the side of this flat plane, you don't see yourself. The waves bounce up away. Whereas if you something circular, you imagine the mirrors on the London Underground that are curved and spherical. You can stand at multiple different angles around and you can still see yourself. Therefore, flat surfaces are good. Then we come to materials. So you have radar absorbent materials. Normal metals that you might build an aircraft out of reflect like those mirrors, whereas other ones, such as carbon and ceramics, absorb it as heat. If you cover an aircraft in these, you get a much smaller radar signature than you would do otherwise. There are other materials which do this to some extent. You can almost imagine them as see-through acrylic or glass, where if you look for it, it's there, but the majority of that wave is going to go straight through it. All of these contribute to, or can be measured as the radar cross-section. So you imagine it's the return that you get from that radar, and it depends on lots of things, such as frequency, distance, the angle that the beam hits you. But fundamentally, and this is where my paper plane looks, if you look at it from the front, it looks very small. If you look at it from the side, it looks very big. That's my 10-minute explanation on this. Then we come to emission control. So leading edges and engines get hot. How do you reduce that? You can either disperse the heat or you can cover it, much as we've seen in Ukraine at the moment, with Ukrainian soldiers using umbrellas to hide their infrared signature from FPV drones above them. It's the same thing. And then we get to digital stealth, which is moving away from physical now. And this is quite interesting because it gives you the ability to adapt. If you imagine you're in a dark room and someone is shining a laser at me, if I were to shine a bright torch back, you don't know how far away I am, you know the direction, but you can't range me. Or the only way that I'm going to find where you are in that room is where you're shining that laser from. So if I threaten you, you've got to switch it off. And therefore, you can effectively stop people from seeing you. Right. Why is this happening anyway? Because if we go back to World War II, radar improvements were advancing so quickly and so well that the 1946 Kármán report in the US said that there were no means possible by which an aircraft could be rendered invisible to radar. Yet by 1960, when Francis Gary Powers got shot down in his U-2, conventional methods of beating surface-to-air missile threats were failing. So the CIA and DARPA launched an investigation. The CIA did this in the Cuban Missile Crisis. So they wanted to know how big does something have to be for a Russian radar to pick it up. Well, what they did was they took metal balloons and launched them from submarines off the coast of Cuba. And they monitored the Russian response until they picked it up. And then they knew how big something had to be. That, along with DARPA running trials with radar absorbent materials and on the shape of aircraft, allowed them to come to a figure. However, the issue here is that, say we were detected 200 miles away normally, and we want to limit that, so that's the price again, so they can only detect us at 20 miles. That is a 10-time decrease, but requires a 10,000 times decrease in radar cross-section. That means making an F-15, for example, half the size of this piece of paper, which is not easy. And in order to do that, many manufacturers were still using clay at the time or wood to model prototypes, but computer modeling was the key. But to do those models, you need the mathematics behind it. And the mathematics come from Russia. A Soviet PhD student called Pyotr Metsev had been studying electromagnetic wave diffraction on 2D and 3D bodies, critically edges. His paper that he published went unnoticed for 9 years until the US translated it and found it as the smoking gun. But it was a smoking gun because you can't just cover an aircraft in radar absorbent material. You can't take something not stealthy and redesign it. The dirty bird here was a U-2 that was designed covered in material, and although it did work to some extent, it drastically reduced performance. And the key thing that was found was that stealthy aircraft, truly stealthy, needed to be designed based on physics far more than aerodynamics. And that presented an enormous problem. And it's a problem that Lockheed Martin Skunk Works took, and they created a design using of Metsev's theories and computer modeling to create this out of flat planes, mainly because their computers couldn't handle anything more than that. But it was called the Hopeless Diamond. And this had a radar cross-section 1,000 times smaller than anything they had previously designed. That model was built, they then took it to the range where they had a pole-off, where they compared it to the other manufacturers' models, and it won by a mile. They were so good, in fact, that they even designed this pole that it's mounted on, because the pole it was on previously had a radar cross-section far bigger than the aircraft itself. If you look at it head-on, its radar cross-section is the size of a ball bearing. That then gave way to Haze Blue up here, which is the flight test aircraft, and notice the inward canted tails, which hides the infrared signature. Then we come on to the F117 Nighthawk. So it looks very similar, and this was the in-service version. And you can see the outward canted tails now. Why? Stability. This aircraft needed to be designed by computers, but it also needed computers to be able to fly it. So those aerodynamics changes were crucial for it to even fly. But then we see the exhausts have to change as well. Mounted above over here to keep the infrared from being viewed from the ground over a wide area to disperse it as much as possible. We see the shapes of the aircraft, we see that, and it's covered in radar absorbent material. Even the cockpit, because otherwise the pilot's head would be the biggest thing that you could see. This was a perfect example of physical stealth in an aircraft. Then we come to the V2, Northrop's version. So after changes to the requirements for a stealthy platform that could go further, that could carry more, and most importantly, nuclear weapons, they redesigned their flying wing idea to have fly-by-wire control, and they won the contract. However, that's where the problem started. You see, this aircraft required intensely complicated computers to be able to fly. It required to be covered in radar absorbent material, which was expensive and fragile. It needed materials that were still being invented. It needed sensors, and it needed a new way of thinking. Wrap all of that up in secrecy, and this cost skyrocketed. And it went from 100 orders to just 21 in the end. But this aircraft was a complete representation of all of those elements of stealth for the first time. Secrecy is one of the things that's been both a blessing and a curse to stealth. And it's a curse because of this thing here, the stealth ship. You see, the stealth ship project was so secretive that generals at the time in the Pentagon didn't want to use it, didn't want to champion it, because it meant no exposure and therefore no career progression. And so it died a death. But stealth still lives on, so you can see the modern class of destroyers there, but they have to be careful, because in this case, these ships here, this one, was so stealthy that where you'd expect to see reflections from waves, you saw nothing. And so the absence of any radar return at all meant that there was something there. Then we see the digital progression with the F-22 and the F-35. Those digital enhancements get better and better, allowing offsets to the physical side, so that they can then compromise to make them more maneuverable, so they can reduce cost and then scale up, which is where we see these. And then finally, one quick mention is this, which doesn't look like it, but it's a stealth helicopter. This was used in the raid against Osama bin Laden, and within this, it's the only picture that exists of the wreckage, but not much else is known. But that is another story. And to end, we have the cat and mouse game, because as radars get better and responses get quicker and more lethal, we see that we need to adapt better. Stealth now comes from the digital realm just as much as physical. And as we continue, we need to know how to beat. How do we know how we need to beat it? Just like with the balloons back in the Cuban Missile Crisis, we need intelligence and sensors. And those intelligence and sensors are what are driving key programs like the Global Combat Air Program for us to be able to develop this even further. Very much. Questions now?
5 minutes of questions.
5 minutes of questions, great. Okay.
You mentioned modelling.
Yes.
And I'm just interested in all of those evolutions, all of those changes in geometry, the evolving threat, everything else.
Yeah.
How do you see the significance of accurate mathematical modelling to support this activity?
It was one of the issues in the initial development of the stealth concept. The modelling was the key, that to be able to understand the shape and be able to test that. So Northrop Grumman, for example, developed their prototypes just through clay. So the director at the time always had a ball of clay in his pocket that he would use to make ideas and put those back. But the issue was that relies on aerodynamics, and that's how people are taught to think to begin with. So it involves a modelling approach, but also the way that you think, because they went for this flat wing, but because it was flat, it needed aerodynamics to fly. And that jagged tail that we saw in the end with the B2 had to be changed, because to begin with, it was just flat to fly, and that caused problems. And so as we started incorporating the computer design and the computers to be able to fly it as well, we saw some really significant changes. And then in the future with this as well, we've seen sensor fusion, and we've seen the power of actually using computer models to be able to develop
far more quickly than we would have done just with prototyping and testing. And so as we go through that, this is infinitely more complex than those have been previously, and it's even more important than it would have been then. Okay.
On a similar theme, I inferred from what you said, stealth of didn't really sort of exist until paper that you described in 1960.
1960. Is it that?
Yeah.
Yes.
Is that fair? Because things like flying wings have been around
So
time before.
that paper
Unlocked the key to be able to design in a new way. It allowed them to model what they were already seeing and therefore develop much more quickly. As I've just answered with the modeling question, that allowed them to rapidly speed up their development. I mean, they even sped it up even more because they thought that the Russians had had that information for 9 years, which they hadn't. They'd ignored it. Before that, you already had the U-2 experimenting in its dirty bird configuration with radar absorbent material. And even with DARPA, they had been experimenting. They had something effectively like Cessna 152, slightly smaller than that they'd made remote controllable. And they were testing it built out of plastics, covered with radar absorbent material over the engine bay as well. So the idea had been around for a while. But the problem was that until that paper came out, which turned the tide, it simply wasn't worth it. Aircraft were still being designed for aerodynamic performance. And if you cover it with a load of material that isn't aerodynamic and creates a load of drag, the U-2 went down from 70,000 to 65,000 feet. It lost 600 miles of range just because of this covering. When it relies on flying higher than enemy missile defenses can get to it, it's not a solution. And so Kelly Johnson of Skunk Works at the time just wrote it off. So it existed, but until that paper changed, until that paper unlocked the modeling environment, it simply wasn't worth it for what they could build at the time. All right.
That with the subsequent designs following the V2, for example, the F-22 Raptor and later the F-35, the JSF that was later known as the Lightning II, that it transitioned, the development of stealth technology more transitioned to what you call digital stealth, where it's more about spoofing the radar with certain techniques. The F-22, as you probably know, how much would you say aerodynamics or perhaps the ability to fly factors into it? Because obviously you mentioned that putting the radar absorbent material on the F-117 and the B2 and then utilising excessive curvature or jagged edges, as we saw with the F-117, it made it pretty much impossible to fly even without the fly-by-wire system that was incorporated. There was one instance with an F-117 on a test flight where the chase plane radioed in and said, "Your tail's come off." He didn't realise it was already compensated for it. Would you say that then that perhaps aerodynamics still factored into the digital stealth evolution because they wanted to make sure they could actually fly these type of aircraft?
Yeah.
And it is still a balance. I mean, we've seen things slightly different. So the roles of these aircraft change. So the F-22, for example, has thrust vectoring. It's a highly capable platform, and it has been built with dogfighting in mind. But it's still got the radar absorbent material or coating over the canopy to stop the pilot's head from being such a big reflector. See from the design and the angles of it as well, that it's got all of it in mind. The problem is that, as I said here, it's a game of cat and mouse, that as our enemies develop, we have to find ways of beating them. And so you have to combine these methods as well. But like with the F-35 doesn't have an inbuilt gun pod. It's not meant for dogfighting. It's meant as a standoff platform. And so it's got a different role to the F-22. But the flyability of these things, it has to be there. There are talks about airmanship, for example, being something that is lost in future platforms. But if you imagine that you're flying in, say, this Tempest, and all of a sudden you lose your electronics, you're in a platform which would be inherently unstable potentially. That how do you, if all of your displays were digital, you have to fly the aircraft even more so than aircraft now. And so that idea of being able to fly the aircraft and airmanship is something incredibly important now. The thing is, it just depends on the aircraft and the role. Okay.
Great.
That's the end of your
Thank you.
Second speaker will be.
Sorry.
Thank you.
Thanks.
Whoops. Good start. Don't think we're allowed to mark you down for that.
Get back to the time.
Okay. Good evening. Thank you. I'm Patrick, but prefer to go by Liam, so there's a bit of discontinuity in that already. Sorry. But anyway, so this is my presentation about ablative-based thermal protection systems and modelling. It's a lot of what I've been working on at work recently, and it's just a massive rabbit hole. I could speak for about an hour on it. So the first thing about me, so I'm from Hitchin down the road, but I moved to Queen's in Belfast to do my degree. Joined Short Brothers back in 2023 to do aerodynamics my placement year. Then did aerodynamics with the Thales for my final year project, and then moved back to Shorts in September last year to go do more thermodynamics with aerodynamics and stuff as well. So I'm combining a lot of it in, as you see, with where do I move at the end of this. So ablation, what is it and what is it used for? So it's charring as material, so it's a form of thermal protection. It's an expendable thing, so quite mostly used on single-use aircraft, whether that be, spacecraft. For example, the Artemis II, that has a lot of cork based around the the core stage, a lot of it, and I've been using a lot of their research and their papers to help for my modelling. So it's a good link into what's going on in the world at the moment. So re-entry vehicles, the Apollo Command Module. So the picture on the right is a cross section of it, as you can see here. So we've got what's actually charred here, and then we've got bits that haven't charred yet, and then main sort of just honeycomb as protection. As you see here, so we've got the flux coming in, so that's your heat load and measured in watts per meter squared, and then you see, so it causes the hydrocarbons, for example, because it's cork, it's natural, and it causes them to decompose, and it releases gases from that. As you see, we've got the pyrolysis gases coming out, and then we have three main sections really. So we have what's charred, so that is the burnt stuff at the top, a pyrolysis region, so it's undergoing that, and it hasn't fully gone into the char region yet, and then we've got the virgin material left underneath. As you see here as well, even though it is charred, it's still very thermally structurally sound, so it will shear off with wind, as we'll get to in a bit later, but it can remain on, and the char itself remains with quite good thermal property. So you don't just want to burn it all off, you want to keep as much as you can on, because it itself, actually looking at some of the studies, the char itself can have better thermal protection qualities. So this is what I've been doing. So ablation modeling and difficulties. So I've been using a finite element model. So it's essentially a grid with different nodes connecting to, and it's represented in my case with 3D here. So I've created just a very generic cylinder. It's not based on anything. It's just taking the modeling methods and applying them to things that I want to look at. So I'm using ANSYS Thermal Desktop, which is what NASA used themselves. They've had a massive hand in help developing it. So once again, Artemis II uses that, and I've been looking at that. It's been quite cool to see it launch and see all their research go into real life. So there are two approaches. You've got the Arrhenius equation, our heat of ablation. So the Arrhenius equation is it's a rate of change where K is, and so we've got bits that we've got. E is the natural logarithm number. EA is the activation energy, so this is the energy per unit mass, essentially. It's in moles, which is the chemical number, and then underneath you've got the temperature and the gas constant. That A it's a pre-exponential factor. It's not something you can just get you just not something you just know. You have to find it out, and that's the same with heat of ablation as well. You've got the overall flux in over the mass rate change. How do you know the rate of mass change? You just have to. It's experimentally is really the only way you can find it. So in order to validate my results, which I would do experimentally, I first have to have experimental results. It's a snake, going after its own tail. But thankfully, Amarim, who are a massive supplier for these out in Portugal, the materials team at work got in contact, and they provided this spreadsheet. So we have different heat fluxes in of kilowatts per square meters, and then test duration and mass loss. And from there again, I've got my mass loss rate, I've got my flux in, I can calculate the heat of ablation. So it was roughly 10 to the power of 8 kilojoules per Kelvin, which is a lot higher number than I was expecting, which made me very confident, because what I was looking at, it was all ablating far too quick for my tests, and any applicable things that may go on were seeming not very possible, because the scale that we are working on is a whole lot smaller than what NASA do. So I was looking at 20 mil of originally, so different thicknesses. 20 is a sort of nice thing we want to look at. So we're looking at hypersonic conditions here, Mach 5. The free stream temps are in the region of 1300 Kelvin, so a very inhospitable environment, but thankfully it's not at the point where the gas starts to break down and ionize. There's not all these other bits we have to look at. So we've got recovery temperatures, so that is that's take it from the free stream temp, and then after all the shock waves and stuff at the front, and then we've got at what skin are. So I had 3. So I had the tip, about a couple of inches of that, and then the cone I made, which are the different recovery temperature and heat transfer coefficient, and then the main cylinder of the body. But yeah, it's just generic, so anyone has an interest that can go home and work this out if you've got access to the software. So way I did it is, so I've got a diffusion node inside, so that's to measure internal temps as well. So I ran it for 10 minutes, and as you can see here, that it actually ablates not that much at all. So for 10 minutes, of which a good chunk of that is at hypersonic conditions, we're only getting 1.2 millimeters of ablation, which is quite good, really. Didn't expect it to be that good. It makes it look like you don't need as much cork as one would initially think. If you're going 5 times the speed of sound, you think that's not possible. But another thing I should mention as well is you can only, with the software, another difficulty is you can't simulate all 3 layers. It either has ablated and it's gone, or it's not. So that requires some thinking as well. So for on the sense of conservation, and we're going to overestimate how much we need, I treated it as once it reached char, we're just going to assume it's been stripped by the wind, it's gone, releasing another pyrolyzed layer underneath. And as well, because I can't do the 3-phase, what Amarim as well provided the specific heat and the thermal conductivity throughout, even through the pyrolysis zone. So I just modeled that as it's the virgin material, because there's not much you can do, and it's still going to remain as one solid thing. So you can see here as well, I'm quite glad my results were concordant. We have been looking at doing some fire testing, pretty much just getting a sheet of metal, sticking some cork onto it, setting on fire, and then see how close our results are. But the only thing is, how to really prove it is we have to make something like this fly, which this is all R&D really. It's not much I can do about that yet. So the validation results I've touched upon, and the in-house testing. The plan as well, as you can couple it with computational fluid dynamics. Anyone who doesn't know, so they're a form of partial differential equations to resolve fluid flow throughout a domain. I quite like doing CFD. I've done a fair amount of it, but I've never done hypersonic CFD. So that presents a whole other thing, and I could speak for hours on that. But having spoken to developers back at ANSYS, because we use them a lot, is a good method would be, so model that as a generic cone like that, and then I can extract about what the results are, the heat fluxes at the skin, and then submit that as map that to my cone. Fluent also has ablation built in itself, but that requires some extra things you need to go and buy, and ANSYS love money. So it would a bit of argy-bargy to get that. But the one most important thing is, will the mechanical properties allow it to work properly? So this is from one of the papers from NASA put out into their public domain about cork testing at the hot gas flow facility. And it was looking specifically at P50 cork. So that's Amarim's one where they bind it with a phenolic binder. So it's essentially a big glue, and it's got 50 micron particles, and it's a sheet, or they make it of a shape you want. And the worrying thing is, you see at Mach number 0.8, all the char is removed by the shear loads. At a mean shear stress of 1.7 psi, that's about 80 pascals, sorry, about 80 newtons of force, which is nothing at all. So then that raises the question of, how do we protect it? Another ablation layer is something. For example, you can get carbon, a simple carbon CFRP layer, that will pyrolyze itself, but it will not be susceptible to shear so much. So that becomes porous as well, and that will also allow the gas to come out and protect it as well. So you need ablation to protect the ablation. It's a very deep topic, and 10 minutes is nowhere near enough to explain it properly. But as we can see, it raises a lot of questions, which I'm very excited to be diving into in the future. But anyway, so that concludes my, oh, too many, sorry. That concludes my presentation. Thank you very much.
Sounds like it's design activities, as always with design, it's a complex trade of competing kind of effects and influences. On one hand, what you've got is a protective layer that has to a degree start to react to those surface temperatures to then provide a level of protection. But you've also to try and put the covering on and to ensure that the covering itself will survive the initial flight. Now, in terms of your work to go, how do you balance those trades? You know, you mentioned the modelling. Does the modelling cover both of those phases adequately? You know, is there a, you know, is it always going to be a combination of some modelling with confirmatory testing? I'm just kind of curious as to how that interplay can be worked through.
Yeah. So generally, overall, like authority relies with the design team. So I would take my thermal recommendations and they will see what they can do with it. At the end of the day, it has to be testing, really. There's no modelling as good as it is. It's a good slave but a bad master. Should never look at something that you've modelled and go, I'm taking that as gospel, it will be 100% correct, because we've seen little bits of errors creep in via different modelling methods, especially with the CP of air, for example. We can see that has affected it, and we've taken it back to ANSYS and gone, that something's not right here. So at the end of the day, we will have to, it's testing, really, is what we have to do. Modelling will only get me so far.
Sounds like you've also worked very closely with the tool vendor.
Yeah, so I have, we have the developers on call, basically. So we have a few meetings with them every so often to help us understand software and where they're going with it, and which will help us. So it's a lot of customer and engineering collaboration, really.
So how was the work you're doing looking almost purely at the material and material behaviour, or were you looking to see how the change in the materials in chars affect other properties, such as aerodynamics or transparency, as it seems to things like art?
So this is purely a material basis at the moment. Yeah, it's more knowledge capture for how we might go down this route, because we're not at the level of being able to just know everything. There are some aerodynamic studies similar, but it's not. That's not me. I'm looking specifically at the thermal side of things.
As opposed to ceramic.
Cheap and easy. It's because it's one of those things that if we're going to do development work, it's something we know what we can do. It's quite straightforward. We know the conditions, or we can know the cork will work this much, we'll bolt it on and go.
Yeah, I wasn't sure the room was allowed to ask questions as well as the.
Absolutely, yes, it's really allowed.
It kind of is a similar question I was going to ask about if you could see ablative materials finding widespread use in hypersonic vehicles, considering how it would change the aerodynamics.
Well, it depends on what the application is. For example, if you were to put like a coated layer, say you put an ablative layer behind a standoff panel, for example, so that would work from my other bits of work I've been looking at. But then that's now difficulty with manufacturing and design. You have to being able to replace that. But even though it ablates, if you don't lose the cork, if you don't lose the char layer, in theory, it's usable again because the thermal properties are still there, so it would work. The widespread use for hypersonic vehicles would more be one-way effectors, in my personal opinion, though.
Thank you. I think that's all about.
Okay, thank you.
Third speaker, Thaabit. Okay. Magnetic backs if you just take it.
Hello? Hello? Can you hear me? Yeah, okay. Good afternoon, everyone. So my name is Thaabit, and today I'll be presenting orbital extension methods for geostationary satellites. All right, let's begin. So just a quick overview of what I'm going to be talking about. As I understand, not everyone here might be space related, so you might not know what a geostationary satellite is. So I'll introduce that, and then we'll be talking about life limitations and why we want to extend the orbit of such spacecraft, and then we'll be talking about the methods. So what's a geostationary orbit? You may be wondering. So geostationary orbit is when you're 35,786 kilometers above the Earth's equator. And the beauty of this orbit is that if you're at the equator looking up at the orbit, the satellite appears stationary, and this can be used for many things such as telecommunications, satellite relaying. Also, it's used for defense in space and stuff like that. And the orbital period when you're in this orbit is the same as the rotation of the Earth, so you're constantly above the same point. And in satellites in this orbit, they have to stay within a slot tolerance of 0.5 degrees latitude and longitude. What that will mean, I'll show you in the next slide. But basically what it is that each satellite has to stay within a certain margin. And if it strays out of that margin, that is, it's not acceptable normally conventionally, but legally it's all right. But everyone likes to stay with conventions. So what limits life in space, you may be wondering? Fuel. Satellites in space, when they run out of fuel, they must be deorbited. How are they deorbited? It depends on where you are. In geostationary orbit, it's the one that we're talking about, they need to be graveyarded. And what graveyard means is it's pushed 300 kilometers out and it's just left there. And the reason why you reach the end of life is because you're using your fuel for something called station keeping. Station keeping is basically small maneuvers you do to your satellite to keep it within its slot. Now you might be wondering, why do you need to do these maneuvers? It's because actually the satellite doesn't stay within its slot. It gets pushed and pulled because of two different things. First of all, it's the Earth. The Earth isn't a perfect sphere. You might think it is, but it's not. It's actually quite lumpy. And because of these lumps, the satellite gets pulled to higher gravitational areas, and that's what causes it to move east and west. There's another thing, the sun and the moon also interact with your satellite, pulling it north and south. And so you need to actually do north-south maneuvers, which actually takes up the most of the fuel. And so geostationary satellites last for anywhere from 5 to 15 years, depending on your missions. So you might be wondering, all right, why don't we just graveyard it? Why do we want new satellites? So the reason is, one geostationary satellite can cost anywhere from 250 million to 500 million just to build. That's a lot of money. So when you build these satellites, you want to maximize your revenue. Revenue from a geostationary satellite is also a lot. You can make up to 200 million, even more, depending on what your geostationary satellite does. That's a lot of money. So increasing the life just by a couple of years means you're making hundreds of millions of dollars, that's one great reason. Another one is, so if you remember in the slide before, there's slots. Because geostationary orbit is actually, it's actually really small. It's only 150 kilometers wide. So it's not that big. So you really want to keep your slots. So if you actually don't have a satellite in your slot, someone could come and take it. It's free for all if you leave it empty. And so that's why you really want to leave your satellite up there until you can either send one to replace it or just keep it up there if it's working and you can find ways to keep it going. And then also, launching satellites is not great for the environment. There's a new push in the space industry where you want to minimize your space debris. And so when you send a satellite into space, there's always a bit of space debris and you don't want to do that. So just having it up there, that's great. Also, launch vehicles aren't great for the environment either. So you want to look into that as well. So now we're going to be talking about our extension methods. So there are 4 that we're going to be looking at. The 4 we're going to be looking at is mission extension vehicles, in-orbit refueling, inclined orbits, and fully electric satellites. Okay. So the first one, mission extension vehicles. What's a mission extension vehicle? Think of it as a tow truck. What it is it's a small satellite that goes onto your bigger geostationary satellite, and all it does is it handles your station keeping. So it doesn't interact with your payload. Your satellite is operational, but it doesn't have to do any of its maneuvers, and it doesn't have to do the north-south maneuver, which takes up most of its fuel, and the other ones as well. And it's great because it can slot onto your engine nozzle, and it just works. And this has actually been tested by Northrop Grumman in 2020, and it actually completed its mission. And one of these satellites can go on for numerous years. I'm talking about the mission extension vehicles. It can stay for 5+ years and do all the maneuvers. So 5 years of revenue is great. And when it's done, if your thrusters don't work, it can also it can also do its end of life maneuvers, which is putting it into graveyard, and come back and carry on with other satellites. So one of these vehicles is great for the industry. Another one, in-orbit refueling. So this is actually a proposed mission by Orbit Fam. The reason I use it is because this idea is actually quite cool. But what it is basically you're refueling your satellites. So what it is, sorry. So right now, actually, there are services where you can send fuel up and refuel your satellite. But this one it's literally in space, and your satellites come to it, or it goes to your satellites, and you can refuel. So now you have a satellite that can go on indefinitely until its components break, which might take longer than running out of fuel. And it's great because now you can do whatever you want with your satellite. You're not conserving any fuel. You can do all your maneuvers. Now there's debris, you can move out the way. And you can even maybe move orbit slots if you get that, which is also the reason why this is important is because, does anyone know about Starship? So Starship is as a rocket that Starship is that Starlink are trying to make. And what it does is that they want to launch it into space empty without fuel, and then they'll refuel it in space. But there's no gravity in space. So to refuel it in space, they have to use centrifuge forces and special pumps, which actually is quite challenging. So that could be but it's been tested quite a lot, so it should be all right. Next one I'm going to be talking about is inclined orbits. So what inclined orbits is quite simple. You just stop doing the worst thing, which is your north-south maneuver. And that means your satellite starts shifting up north and south, as in the name. And it shifts about 1 degree a year. This is great, and it's actually the most used mission extension method right now because it's easy. You just stop doing a maneuver. So what happens now is that you're no longer actually in geostationary orbit. You're in inclined geosynchronous orbit, which means you actually have a figure-of-8 ground track. I'll show you in the next slide as well. And the reason why not all satellites can do this is because, does anyone know what that is? Your antenna in your house, that's fixed. Now that your satellite's moving, it won't be able to track your geostationary satellite. Well, it's not geostationary anymore. So that's why it's used. But it's going to get a bit technical now. Also, because you're not in geostationary orbit anymore, you have to reconfigure your beams because you're not perpendicular to Earth anymore. You're at an angle. And that needs beam reforming, which is actually just simple recalibration. But there's a bit more complexity. So when you're inclined, you want to be pointing at the center of the Earth, not the center. You want to be pointing at the equator for maximum coverage, but you're actually pointing at the center of the Earth. So you need to apply something called a harmonic bias. All right, a harmonic bias basically is where you spin your momentum wheels, so you're pointing at the equator. So now your limiting factor on how inclined your satellite can go is these wheels. How much momentum capacity do you have So you can spin your momentum wheel so you're pointing at the Earth. So there's actually ways to increase this. One is you can use your redundant systems, or you can actually reduce your momentum you use for your maneuvers, and you use that for your harmonic bias, so you can increase the duration of your mission. And this is a trade-off that different companies will have to look at. Also, another issue is that if you get, let's say, all the way up to 55 degrees, you might no longer be able to see your geostationary satellite because it's really a big angle. So that's something when using inclined orbits. The final one I'll be talking about is fully electric satellites. So in conventional, well, olden satellites, almost half of your fuel is almost half of your mass is used on fuel. That's not great. That's not great at all, because fuel is very bad at burning. Well, it's great at giving thrust, but the efficiency is horrible. So you get electric propulsion, you can get almost 10 times more thrust per unit than in chemical. So you really want to be using chemical boosters. So now the industry as a whole is actually moving towards fully electric satellites, and that's why you want to use that. But however, there is a trade-off, because now your thrust is much less. So to get to geo orbit, it takes a couple of months instead of days or weeks. So, but also electric propulsion, it still actually uses propellant. It's actually xenon, and so that's still a life-limiting factor. Anyway, thank you for listening. So this is a summary of what we listened to, and I hope if you have any questions, please let me know.
You were mentioning the satellite as it goes out of geostationary orbit, and you're trying to then maintain that sightline to the equator. You mentioned a thing called momentum wheels.
Yes.
And I had envisaged, is this physically kind of rocking the satellite to maintain the sightline on the equator? What is that?
So we have two wheels or spinning wheels in your satellite. One is a reaction wheel, one's a momentum wheel. So we use a reaction wheel which spins and it changes the orientation, and a momentum wheel keeps it like at where you want it to be to conserve momentum, because it's just spinning in space. And so Newton's third law, every action has an equal and opposite reaction. So with it spinning, it'll keep your momentum where you want it to be looking at, instead of trying to move back to the center of the Earth. Yeah. Okay. No problem.
You say there's no one single best best solution for mission extension vehicles or solutions for geostationary orbits. What's your opinion on the best solution?
So actually, I can tell you a story. So now I'm actually working at Airbus right now, and I'm working on a satellite launched in 1990, and it was a 5-year lifetime, but it's still operational. That's 36 years old, and it uses inclined orbits. So depending on what you want your mission, so if you're, let's say, a telecommunications satellite where you can't be moving a satellite, you wouldn't be able to incline it. But if your mission allows it, inclined orbits are technically free. So, and you don't have to do anything to your payload, anything to your satellite. So if you could use inclined orbits, that's great. But that's why I said it depends on what your mission is, because some missions you can't do that. So yeah, that's like, well, it was on my last slide, but yeah, that's like, in theory, there isn't. But if let's say fixed antennas aren't your issue, inclined will be the best way to go, as most satellites do it.
The money that can be made from subscribers to your satellite service, but if you start out with a geostationary satellite, then you transition into one of these inclined orbits. Is it true to say that your subscribers to that satellite are going to have to change? It's a different market. So because the people who have fixed antennas pointing at a geostationary source will no longer be able to actually point at that satellite. So is that part of the equation? Thing of the satellite to a different market.
So that's also another story I can tell you, but yeah, that's also true. So one thing I didn't mention geostationary satellites can't actually look at the equators when they're geostationary, but when they're inclined, they can, because they're now looking a bit higher. And so actually some of the satellites I'm working on now is used in Antarctica, in the North and South Pole, to communicate with people up there. That's like, you can shift markets, but also you got to think about who you're selling it. So if you're a TV broadcaster, you can't change your market. Your market's still fixed. But if you're a defense company who wants to do communications, most people, like, let's say if you have a ship using a geostationary satellite, your antenna can already move because your ship's moving. So it's not greatly impacting the fact that you're inclined. So it really depends who or what you're trying to do with your satellite. But yes, short answer is yes. You can change your market.
Just a quick question. So with the mission extension vehicles, or I guess even the is the concept that's sort of one extension vehicle per satellite, or could you have a system where one extension vehicle moves between the satellites? So
when it comes to the mission extension vehicle, there are many different types. The one I talked about is just, it does its station keeping. So if in that case, the station keeping one, after 5 years, the satellite will be probably around 20 years old, 30 years old. It's quite old. If you think about your phone 20 years ago, it's quite, so you might want to already change your satellite by then. That's why it's around 5 to 7 years increased period. So there are different things you can do with it. So there, like I think I put it in my slide, it can leave your satellite and go to another one. And then also there's another concept that ESA's working on right now, which is an arm. It just goes up and, like, if there's a component broken, it fixes it, and then it'll go and basically fix other ones. So, but yeah, it docks on, helps it, and then docks onto another one, if that makes sense. I can talk after.
Fourth speaker will be William. Sorry. Good.
Perfect, thank you very much. We all hearing?
Right. So for the last few years, I'm sure we've all heard about AI, and maybe some of us, in the aim to boost productivity, have been using it a little bit too much in the office. What is Edge AI, and how will it fuel the future of uncrewed aircraft in defence? Over the next 10 minutes, I'll try and answer that question and highlight some of the key challenges involved in the technology. So let's start with what Edge AI actually is. So the AI we will be used to, like ChatGPT, is where you're sending communications to an external data center, and that will have the processing chips like GPUs, and that will perform the processing for you. And then it will send that communication back to you, to your chatbot. Whereas Edge AI, you're downloading the AI model directly onto the local hardware. And that means there's no server latency. So you're not sending your communications to maybe the other side of the world where the data center is. That's increased security because the communications never leave the hardware. And offline operation is possible, making it essential for a defense application where security and low latency systems are essential. So why does this even matter? I started at Leonardo a year ago as a placement student, and one of our introductory training courses, my training instructor, I had a chat with him about AI applications and the future of defense. And he said to me, he believes that the next generation of fighter jets will be uncrewed. Torsten Röhl, one of the biggest, the CEO of one of the biggest German defense startups, said in a Bloomberg interview that he believes it will be ethically problematic to send humans into the sky in the future. So why does this matter? Looking at a current conflict, Ukraine and Russia, since the beginning, this is the beginning of the conflict, so the number of troops at the start, so Ukraine with 200,000 and Russia with 900,000, and the military expenditure about 4 times more for Russia as well. And how have Ukraine been able to be so successful? As well as help from allies, we've seen about 60 to 70% of all destroyed Russian equipment as a result of uncrewed aircraft or drones. And since 2024, the UAV output has risen by 900%. So this is actually a modern, very modern thing, even though the conflict is 5 years old and still ongoing. This is from 2024, and that statistic is from mid-2025. So this is really a modern solution at the moment. So let's get into the Edge AI architecture. So let's look at the current capabilities first, and we'll get into the pipeline. So this is one of the most recent drones launched by a Turkish defense company and being shipped to Ukraine. Using AI, so without any human operator, it can do terrain reference visual navigation, dynamic route planning, and target detection identification. So how do we upgrade the avionics from something that we're seeing right now to a modern fighter jet? Well, let's look at the pipeline first. So the pipeline, it will start with an antenna or a sensor, which will take in the data, and an ADC will then convert that to a digital signal that a processor can understand. The FPGA will take in that signal, break it up, put it into a format that the machine learning processor will understand. And that can then get sent to a mission system, either other drones, if this is a drone swarm, or back to a base where personnel can see that data. So what's the machine learning problem? Right now, that FPGA to machine learning processor is a bottleneck. High-end, low-power machine learning chips can't handle the quantity of information that modern avionics systems require. With a single channel ADC, so that might be one sensor taking 20 gigabytes a second of data, whereas these machine learning processors can only take 4 gigabytes a second of data transfer. So you can see that doesn't quite fit. And this, with multiple sensors, that will actually increase. So we're looking at gigabytes a second right now. This is going up to terabytes a second, trending towards terabytes a second. So we need the FPGA to break up that information, take in all the important parts, and send that to the machine learning processor. So it's worth touching on size, weight, and power constraints. So this is the NVIDIA Blackwell GPU, their latest GPU. And it can take in terabytes a second of data transfer. But it takes 1,000 watts of power to operate, which is just unfeasible on an uncrewed aircraft. Some of the slides have gone.
In this case, I'm going to suggest that we pause this one here, go away, we'll put the slides back together, and if you can pick up halfway through the second half, does that work?
Yeah, it ended off there at a good break point, so.
Plan.
we work together, yeah.
So, I apologise for the slight change in plans. Elliot, are you able to go next?
Yes.
While everyone else gets refreshments, I'll arrange the slides. We'll do them then. Thank you very much. Yes. Expecting 11 slides?
I think so.
That's good.
Hello, everyone, and thank you for coming. I'm Elliot Badcock, and I'm a researcher at Imperial, and I want to talk to you about some interesting physics in hypersonic boundary layers. I warn you, I am a mathematician, but there are no equations in the PowerPoint. So, as Liam was talking about, when the Apollo command module returned from the moon, it hit the atmosphere at Mach 25. That's 25 times faster than the speed of sound. At those speeds, air compresses so violently that the heating at the surface exceeds 1600 degrees. Now, that's hot enough to melt steel. Every re-entry vehicle has to deal with this heating problem. So we have to combat the heat that the aircraft experiences. And one of the ways to do that is with this blunt body. The blunt body pushes the shock wave further away from the body so that the energy heats up the air around the body itself rather than the surface. But that's only half the problem. There's still heating on the surface. But the question is how can we limit that? And where does that heating live? So this heating lives in a thin region of fluid around the body. If we imagine the body as a flat plate, this fluid is the boundary layer, and it's this sort of dashed line over the top. Near the leading edge or near the front of the vehicle, the flow is orderly, it's smooth, the streamlines are parallel. This is called laminar flow. Laminar flow is really ideal because it acts as a temperature insulator, so it's cooler. But something happens when we move downstream. As we move downstream, the free stream disturbance waves, so this could be of acoustic nature, enter the boundary layer, they penetrate, they become their own disturbance waves, these oscillatory up and down structures in the boundary layer. They can grow, and eventually they can grow so much that they transition the flow from a laminar boundary layer, that smooth, orderly behavior, into a turbulent boundary layer, which is a lot more chaotic. It's got a lot more rotation. And the consequence of that with heat is that turbulent heating is 5 to 10 times more than laminar. Now, if you're an engineer, if you're Liam, it's really important for you to identify where transition happens on the surface. If it happens close to the leading edge, then you need to put more heat shield on your aircraft, and that can be costly in terms of fuel. If it's further away from the leading edge, then you can put less shield on this. You've got less weight, it's cheaper, and you can run more missions, etc. It's also greener. So we're going to talk about how these disturbance waves grow inside a boundary layer. And we'll start with a subsonic wave. So this is when the Mach number is less than 1, less than the speed of sound. So I'll quickly explain this calculation. This is a calculation that we've done just on a laptop, but they're solving the Navier-Stokes equations. So at the inlet, we've initiated some kind of impulse, and that's generated this disturbance field. This disturbance is oscillatory in space. This dashed line is the boundary layer itself. Now, in subsonic disturbances, there's only one dominant type of wave that can exist there. There's only one. It's simple, predictable. It starts off quite weak. It grows. It then trips the flow into turbulence, and it can decay. So these are very well understood. We've understood them since the 50s, 60s, and it's just called a Tolmie-Schlichting wave. But there's only one. Now, in hypersonic boundary layers, the situation is somewhat different. So this is a calculation of hypersonic boundary layer. So the key bit of information here is that there's multiple dominant waves. There's a fast wave. Now, a fast wave has a long wavelength, and there's a slow wave which has a short wavelength. So one of the wavelengths goes up and down slowly, and one of them goes up and down quite quickly. We've initiated this calculation with some acoustic noise, and we get the fast wave at the beginning. So this is quite a simple structure. It's later on when things get more complicated. But because there's two waves, these waves can interact, and this interaction drives growth that eventually will drive transition and blow the laminar flow up into turbulent flow, which is bad. Okay. So how can this happen? Well, the fast and the slow waves have different initial wavelengths. One is quite long, the other is quite short. As we move downstream, the fast wavelength starts approaching the slow wavelength. And when they match, that's this region here, we get a synchronization. So we have a matching of the wavelengths of these two waves. Suddenly, the slow wave starts to steal energy from that fast wave, starts to snatch as much as possible. And suddenly the slow wave becomes more dominant. And that's this structure on the right-hand side. We see these streaks coming down into the disturbance field. And we have this really weird structure at the end. So how does this happen? Well, these waves are solutions to the Navier-Stokes equations, and that's too much for 10 minutes. So I'll show you a reduced order. Oh, this is where the slow wave dominates. I'll talk about a reduced order model. So I'm going to show you two calculations. One has synchronization, which is on the bottom. The other has no synchronization on the top. We have a fast wave, which is going to be in black, and a slow wave, which is going to be in red. Now I'm going to initiate these calculations, and we'll see these waves start up, and then we'll see the dynamics. The fast wave on the top It's not going to change wavelengths. Let's have a look at that. It worked, brilliant. So an impulse initiates these two disturbances. We can see that the black, the fast wave, has this really lovely periodic behavior. It looks like a sine wave, goes up and down, got fixed wavelength. The slow wave, on the other hand, the boundary layer doesn't like it. It just decays, kills it off immediately. We only have the fast wave. Now, in this bottom calculation, we're going to turn synchronization on. So that means that the fast wave is going to shrink and the wavelength is going to change as we move along the flow. So let's have a look at that. Fantastic. Okay. Yeah, we can see that fast wave start to compress. And as a result, the slow wave has started to steal that energy from the fast wave and has exploded. And it's got much, much bigger than the fast wave ever was. And this is synchronization inside hypersonic boundary layers. This is actually what happens when you have real physical phenomena, but this is just a simplified model. Now, it's similar to some of these resonance problems. You may have heard about these, well, buildings have a resonance frequency, resonance wavelength, and sometimes if there's an external force that's being applied to that building or bridge, for example, that bridge can shake, can oscillate, can break and fall apart. The classic situation is on a tower bridge when you've got soldiers marching in step, and that beat drives that frequency, and bridges can fall down. Or there's a video of the wind doing it to a bridge on YouTube somewhere. Would have been brilliant if I put that in. And this is completely analogous to this case. Completely analogous, except from the fact that there's no forcing here. There's no military man walking on the boundary layer. There's no wind blowing the boundary layer. These boundary layers can have these waves in them themselves. They're a part of the richness of these Navier-Stokes equations that give this beautiful picture that people are spending their lives trying to solve. So I think that's just a really interesting piece of physics. I find really exciting. I don't understand it, but I hope you do. So what is next? So at Imperial, I developed computational methods to try and track these disturbance waves, see where they grow and see where transition happens. And we do that on multiple different aircraft. Cones, we've recently worked with DSTL on the Swift model. I've got some pictures if you can see. And some of the UCAV data. So that's some of the work that we do. If you're an engineer, you care about this because you want to understand where transition happens, how it happens, and if it happens to your aircraft. So we can now compute this, but the question is, can we control it? Thank you very much, everyone. Any questions?
There, obviously, I was kind of wondering, what's the physical effect then of these kind of resonances, where you get this massive increase, like a chirp, for example, and the amplitude increases substantially. But what does it actually mean? You've got a surface which is heating up tremendously. You know, what is the manifestation of that resonance effect within these, hypersonic waves? What does it actually do to the object?
So what this does, and all the calculations here were linear. So these disturbances were really, really small. So what this synchronization will then lead to is real finite disturbances that we can actually see and we can actually model in experiment. And they actually then build and change the nature of the flow and cause turbulence. So if a flow goes from laminar to turbulent when you don't want it to necessarily, well, in subsonic flows, it increases drag. In hypersonic flows, it can increase heat. And maybe you want that. Maybe you want an aircraft where actually there's more drag on the wings, or maybe you want a greener passenger aircraft with less drag. So again, it depends on the situation you're looking at.
So you anticipate a time where sufficient knowledge and understanding of this phenomenon, you could exploit it to some degree in the design, for example, of structures.
Yeah, so for example, you could cause turbulence. So here, I've got the same
calculations before, but at the bottom we've heated the plate, and actually the waves got much bigger, and we've put the onset of turbulence before. The same calculation for a different flow could stabilize it, could kill those waves off. So with clever computing and brilliant engineers, yeah, we could manipulate these waves to do what we wanted. That's great.
Thank you.
So given the budget, then, what would you want to do next? You asked about sort of can we control it?
Yeah, I'd love to do specifically in hypersonics. I'd love to study the computational methods of different ways to control them. So some advanced techniques are to blow more fluid into the boundary layer itself, and to either control attachment, control reattachment, or actually to dampen these disturbances entirely. The reason that's a tricky problem is I've shown you this for one frequency of disturbance. Now, air contains as many frequencies as we can conjure up. So we've got to apply these in clever ways to combat all the disturbances rather than one particular one. So that's what I would love to do. I'd love to study the control of many disturbances at once. So it's not just doing one calculation, it's doing n coupled calculations, and they all talk to each other, and we try and manipulate those flows as we go. So that's what I would do with.
The complexity then of the computation.
Yeah. And how all the individual computations talk to each other. We've got, yeah, go on.
Talking about only frequencies coming out from the fast wave and the slow.
Yeah.
What is it that determines those frequencies? Where that comes from?
So they are acoustic. They're acoustic type disturbances, and when you have hypersonic flight, you create shock, and the propagation of information travels along a cone, and these disturbances are like the top disturbance and the bottom disturbance. So that's a gross oversimplification, but it's similar to in subsonic flow. In subsonic flow, acoustic disturbances go forwards and backwards. So when I clap, over there hears it, and over here hears it. In hypersonic flow or supersonic flow, information doesn't behave like that at all. Some information does go upstream, but most of the information goes downstream in one direction. So if I clapped, most of that information goes that way. A little bit of leakage goes that way. But what we're seeing is the flip of that upstream behavior go that way. And that's what you're actually seeing in supersonic behavior, where the direction of propagation of the information goes in the same direction.
The frequency depends upon the actual speed of the.
They're dependent upon the Mach number. They're dependent upon the equations. Yeah, and the base flow. And so what we're doing here is we're taking known base flow, so a boundary layer flow, and we're artificially putting in tiny waves with some forcing and seeing how they grow or decay. Thank you very much, everyone.
Right. Thank you all very much for your patience.
Sorry about that. I'll try and update you or recap it quickly, each slide. So about Edge AI and the future of uncrewed aircraft. We'll just quickly go through the slides up to where we were before. So we touched on what Edge AI actually is. It's on local hardware. It's downloaded on that local hardware and put into a system. Briefly went over why it's important, where the industry believes the technology is heading. We looked at the current conflict in Ukraine and Russia and how important uncrewed aircraft have been for Ukraine's defense. And we briefly looked at the architecture, the hardware side. So we looked at current capabilities, so terrain reference visual navigation, dynamic route planning, target detection and identification, all controlled without a human. And then spoke quickly about how we're going to upgrade the electronics inside these systems. Looked at the machine learning pipeline, what's currently in use. And then we looked at the bottleneck and the machine learning problem with the hardware currently in use and why we can't use it for the whole system, can't use these machine learning processes for the whole system. And then we looked at swap constraints. So the NVIDIA Blackwell chip GPU, which could handle terabytes a second of data, but takes 1,000 watts of power. So, and now onto the bit that was missing. So training edge AI models, which are going to be more important. Next slide. So neural network training. I've chosen SAR here as an example, just because it's quite easy to see what's going on visually. So this is synthetic aperture radar and provides all-weather image capability. And so a neural network, we fed data before emission, and that will be maybe images of threats that it might encounter on a mission. And then so when that's been downloaded onto the model, when it's in flight or on the mission, it'll be able to spot those threats and identify them and act on them. This is what we call an open loop algorithm. So this is where the model is trained on a fixed data set before flight, and then that data set doesn't update at all during flight. Whereas in defense, where we have limited data, we don't know if countries are using all of their equipment until wartime starts. We need a closed loop algorithm, which is an algorithm that learns and updates based on experience and during a mission. So how do these closed loop algorithms train on flight? So closed loop training. So an algorithm will detect and determine if an object is unknown. This might be the open loop algorithm, and it won't be able to match that image to anything that it currently knows. That unknown object will then be labeled. So this might be unknown class 1, and then a confidence score will be applied to the labeling. And I'll get onto that onto the next slide. And then those newly labeled examples will be put into the training data. So that means if unknown class 1, we don't know what it is yet, but if there is a threat that's been encountered that is very similar, then that can be, you can start grouping these unknown threats. And so you might have unknown class 1 and unknown class 2. But what do we do with these unknown classes? So next slide. So one thing that's currently being researched is LLM transformer embeddings, large language model transformer embeddings. So what is this? This is where the neural network will map a 3D plane of space based on characteristics. Each object will be plotted based on characteristics. And so then unknown objects, those characteristics can be extracted from data from sensors on the uncrewed aircraft. And you can actually plot those sensors, plot those characteristics closer to other objects. We need this because neural networks are very bad at generalization. What does generalization mean? That means if you showed someone who doesn't know anything about jets and you show them an F-35 fighter jet, they'd also be able to know that the Eurofighter Typhoon is also a fighter jet. Whereas a neural network, if it's only trained on Typhoon data, it won't be able to identify the F-35 as well. So unknown objects can be identified by association. Yes. So what's the future direction? Next slide, please. So we looked at the machine learning pipeline. Next slide. And so ideally, we take out the FPGA, this bottleneck to the machine learning processor. The hardware also needs to improve. So currently, this machine learning hardware one thing that's being looked into is photonic hardware. So that's using optical waves rather than electrons. Photons rather than electrons to process information. And then we need improved closed loop algorithms. So we need, with an increased number of sensors and sensor resolution, we'll be able to have more characteristics where we could plot these objects on that transform embedding that we spoke about. The problem with closed loop algorithms as well in a defense context is because they're updating during flight and and a human isn't in the loop, we don't know how they're going to act after a long mission. So they're very hard to test and validate and get certification for. So that's why it's very hard to have these closed loop algorithms put into these systems at the moment. Next slide. So just to summarize, these were the current capabilities that we have on uncrewed aircraft or drones. And then next slide. And then this unknown threat detection and identification will feed into every section of operation that we have at the moment. So for example, dynamic route planning. If we spot a radar that we've never seen before, or we don't know it's a radar yet, we spot a radar that we've never seen before, and we actually plot that on that transformer embedding very close to another radar, we can make an educated guess that it might be a radar, and we can update that route to avoid it. That's just one example. Next one. So while most of the information I got was talking to researchers at Leonardo looking at machine learning and implementing it into technology at the moment, I did put down a couple of sources for information that I got in some of these slides. Thank you very much. But please don't ask any questions.
Your description passed over quite a few different techniques in there. You talked a little bit about machine learning, large language models. We talked about artificial intelligence, and I think some of the applications seemed a bit more like exosystems to me in terms of the way in which they've been developed. So, based around a variety of applications that a future aircraft is likely to encounter, do you see all of those techniques in some way playing a part? So not just Edge AI, but a collection of different techniques being variously applied.
Yeah.
Maybe you could tell us a little bit more about your thoughts on that.
That's a good question.
So yeah, you're completely right. We don't need machine learning for every single application. So this would be part of a big ecosystem in the device. So currently we have radars that can spot threats and identify them without machine learning. So that could be put into the process, and then that data gets sent to the machine learning processor, and then that machine learning processor can act on that data. So yeah, we don't need machine learning for absolutely every single part of it. We also have filters as well, filtering out signals and to reduce the quantity of data that we're passing on to that machine learning processor. Yeah, it's a good question. I hope I answered that.
No, I think it sounds like what you're saying is that it's trying to then tailor things according to the application. Yes, we're just on that journey at the moment, trying to determine which application, which technique suits which application most effective.
Yeah.
Exactly.
So from the research that you've done, it seems that there is a school of thought that the next generation, i.e. the seventh generations, the fighter aircraft may be more likely be uncrewed, unmanned. But there is, I think, historically, there has been a debate over how much automation you can let into an aircraft.
Yeah.
The basic argument is passengers at the moment, I don't think, would be willing to fly on an airliner that has no pilot, even though statistically a large percentage of incidents or mishaps are caused by pilot error. But the counterpoint to that is that whilst improvements in processing power mean that AI can, large language model AIs and artificial intelligence can accomplish more functions. Fighter aircraft fighter aircraft, by the nature of their roles, have to be adaptable, and so do the operators. Do you see? My question is boiling it down. Do you think one of the technologies that you've described, or a mixture of those, could they truly replace manned aircraft in most engagement situations?
Yeah.
I think you're touching as well on like the ethical side of things as well. Like, can you have AI pull the trigger as well, on a lethal side as well? So Yeah, I think that's a very complicated topic, and the ethics, maybe I won't touch on it too much because it's a very complicated topic. I think with a lot of these applications with terrain navigation and object identification and surveillance, because it's non-lethal, the ethical considerations are almost, because you're not pulling the trigger necessarily, you're doing non-lethal operation. So it makes it a bit more ethically okay to use that as automation. But I do agree that that is a very complicated topic with some of the fighter jets that we have now. Can you automate that?
Yeah, I think what you're saying, initial stage, going to see AI take over a lot more of the passive, or as you say, the non-lethal functions. I think we're still a ways away from getting AI to pull the trigger by themselves against another manned threat, for example, because we already have UAVs releasing weapons in combat or being weapons themselves. And it's not so much the technological things you say, it's more the ethical.
I think with the discussions I've had right now, machine learning is put into very specific contexts, like you were talking about as well, where it's used in very specific scenarios where it is helpful. Yeah.
One of the potential risks in this area is fragility depends on the data. So when you deviate, when you present a trained network with a sample which does not directly correspond with the data upon which it was trained, the way in which it degrades can vary from, gradual to catastrophic quite quickly, and that plays out. So I wonder, in your discussions with, your colleagues within Leonardo, I've kind of views that you've formed on that particular aspect of the use of AI.
Yeah. I think I haven't looked at that particular topic. I do know that during a long mission, these models can degrade if they're iterating the learning process. But with this large language model embedding helping this generalization problem, where if it hasn't been trained on this particular object that is identified, it can plot it based on its characteristics on one of these 3D planes of spaces and then make an educated guess. And that educated guess might be attached with a confidence score, so how correlated it is to something else as well. So then you could say this is 80% likely to be a radar system. Yeah.
Thank you.
Thank you very much. Yeah.
Final speaker will be Sam Gold. Speaking.
Is it a clip or?
You'll have to ask Will to do it.
Okay, should be fine, man.
Old school words. Yes.
So, hello, my name is Sam Gold, and today I'm going to be presenting on 3D printing in space. Next slide, please. Works. So, a basic introduction over the course of the presentation should go over the basic history of 3D printing in space, some of the capabilities, manufacturing processes, some of its uses in the medical field, and possible future uses one day. Next slide, please. So, big old question, why bother in the first place? To put that simply, some of the reasons are, just one more click. For the most part, it comes to reducing cost and saving time along with safety. Overall, resupplying tools, parts, bits that break to the International Space Station costs a lot of money and overall a lot of time. Being able to print it in space instead of taking months and millions of pounds, it will take a day, an hour, and the material cost of bringing it up there. Of course, there's also researching some of the effects and also minimizing some of the risks on longer space missions where you won't be able to get resupplies. And of course, then deep into the future, being self-sustainable on other planetary bodies. Next slide, please. So starting at the very beginning, the 3D printing in zero-G experiment project. This started in 2014. It was done by Made in Space. Overall, it was a FFF printer, which is essentially pretty much like most Earth printers, where it'll just be printing filament out. It'll be heated through a nozzle, and then it will, layer by layer be built up to build a structure. The material used was ABS. And some of the things that were printed included the very first thing ever printed in space, a faceplate of the extruder printer head, which is on the slide ahead, some of the calibration prints, a few of the test prints, a few useful objects, and this. This is a bit special because for two reasons. The ratchet wrench, one of them being probably the first tool ever printed in space, the other being the first 3D print that was sent from Earth to space. All the other ones before were downloaded in the actual printer. So it kind of shows capability of being able to do a lot of the work from ground control and then just taking out on the International Space Station. These samples were taken back in 2015 and compared to some of the Earth prints done. The results of this were, next slide, please. Overall, pretty anticlimactic. One more, please. Overall, there really wasn't much of a difference between density, mass structure, weight, or the compression. There were a few differences in some of the first tests, but this is mainly due to a miscalculation with some of the print settings and calibrations. Further testing was then done in 2016 that then proved that there really wasn't much of a difference. The main reason of this is due to some of the properties of FF printing, being that most of the effect of the print actually comes from adhesion to the plate surface, not actually gravity itself and the properties of the materials. This means when you're controlling the extrusion temperature, it will come out at a stable rate, it will cool down and, sorry. So the velocity, the velocity of the material is quite thick overall, a bit like, I don't know, to say honey. So it will stick to the plate fairly easily, even in zero-G, and won't come off it due to surface tension. And then as it goes on to print the next layers, it will just heat up the previous layer and join them together. So overall, kind of works the exact same way. Next slide, please. Few differences. Here's a few images. This first object ever 3D printed in space. Of course, all this had to be sealed off because the whole area needs to be climate controlled, because when you're 3D printing, a lot of quite nasty gases are released and you don't really want them floating around in space. So you had a bunch of filters in there, sort of keeping everything stable. Also, in case anything came loose, it in this area. Next slide, please. So later on, the AMF was sent in 2016. Essentially, this did a very similar job, just with a larger print volume. Volume, and also was going to be a permanent installment. So instead of testing, this was actually being used properly by the astronauts. It could print in several materials as well, and like I said, it was mainly used to print tools and further research in 3D printing in space. Next slide, please. So getting on to an interesting topic. So why would you bother 3D printing bioink in space? Bioink is essentially, so overall, the main reasons for printing biofabrication facility in space would be due to the fact that on Earth, a lot of the structures that you would want to make, such as vein systems and whatnot, wouldn't really be possible on Earth due to them being hollow and having small overhangs, so they'll collapse under their own body weight. While in space, you don't really have that problem in microgravity. So a lot more of these structures can be made, which then can be built up into realistic organ structures. Also, the cells themselves suffer less compression and less distortion, meaning more cells survive and you have more successful prints. Next slide, please. So this wasn't the first bioprinter in space. The first one was in 2018 by a Russian company. I can't remember the name off the top of my head, which used magnetism in some way, but that was on a very small scale. While the BFF actually is still in use today, unlike that, and has printed more impressive stuff, so I thought I'd talk about it. Essentially, it uses bioink for printing. This is a gel blend of cells and carrier material. This carrier material usually being hydrogels, which was used as scaffolding for the living cells and sort of to protect them as the structure grows. It works by loading the bioink into a print cassette. This cassette is then loaded into the BFF. The molten bioink, when I say molten, I just mean in liquid form. It wasn't heated up because that would kill the cells. Was then pushed through a nozzle, which then presses the layers together. Once this was complete, it was put into an incubation hut, which you can see next to it there. In its first mission, it printed part of a knee structure and a large volume of human heart cells. In 2013, it managed to print a full human knee meniscus. Next slide, please. Sorry for my pronunciation. Right, you'll notice the first metal 3D printer in space came up thanks to Airbus. There's a few of them in the front. Over 10 years after the first plastic one. This is mainly due to there being a lot more difficulties with 3D printing metal in space due to the fact it's essentially acts a lot more if plastic 3D printing acts as a honeyish substance velocity wise. This would be a lot more like water per se. So it would be a lot harder to control. There's also the problem of it needs to go over 1,000 degrees to melt in the first place. And thank you, temperatures in space, hot temperatures in international space stations don't always go together too well. So essentially, it used a laser when it pressed stainless steel into the plate. Then it would actually melt into the plate itself and then build up layers by layers by then. First print made by it was an S-shaped test piece, and overall it has a very similar function to the earlier thermoplastic 3D printers, but of course, it's a lot stronger and can handle a lot more pressure. Next slide, please. So the future of 3D printing, some stuff to look out for. The RRP is essentially a mission to use lunar rock or other planetary surfaces to as 3D printing material. This would then eliminate the need for resupplies in the first place at all. Then there are a few more here. Most of these being biofirst aid, updates to the metal 3D printer, and overall the one day being able to print full organs. And I think I'm about out of time, so next. So these are some of the companies involved. And last slide, any questions?
I was kind of interested in, where do you see the future for this? Because there's a combination of things in here, like, for example, you know, trying to manufacture spares if there was a failure during flight might be one option. But then some of the, you know, the bioprinting and metal printing and all, I was curious as to whether there was perhaps an aspiration that, you know, the repeatability of the processes in space would actually be more conducive to repeatability. Isn't that a longer?
Absolutely. One thing I didn't mention, which I had on one of the last slides, was there's a company working on building retinas. Because on Earth, building up the layers, 3D printing them doesn't quite work because there's too much pressure on them. You can actually do that in space, and they've started manufacturing of that at the moment. I think at least they've sent up some prototypes of that. In the future, they also plan to, eventually get to the point where you can make full organs in space, luckily, so you can send cells up, and then they 3D print an entire structure and then hopefully send it back down. Of course, on the more manufacturing side, it's quite handy if you're building a lunar base, essentially, if you can take, the material around you and then actually build your structures out of that. Essentially, hopefully we'll get to the point that you no longer need real resupplies from Earth and you can do most of the processes independently. It's kind of the, yeah. Absolutely.
Testing with printers on Earth and in microgravity.
Yeah.
They to sort of interpolate what's process would work in gravities in between, the low gravities, the moons, the Marses, the
It's a good question. For the most part, when it comes to things like the 3D, with metal 3D printing, not too sure because it's still fairly early technology. Some of the first tests have only been done in 2024 and they're still getting the results back now. So I couldn't find any papers talking about essentially what some of the differences are. But when it comes to plastic 3D printing, it's very much the case that it's mostly reliant on the material itself. So in different gravity, it should work because there'll be different calibrations needed and nozzles the nozzles actually height will need to be different from the base. But apart from that, I don't think there's been too much testing at different ranges, but it is very much possible.
Any sense like
questions? Yes. Given the sort of techniques you were talking about there, does that mean there is actually pressure to standardize on a set of materials, a small set of materials that can be used for stuff, particularly in the context of, of space station?
No, absolutely. I'd say for the most part, there'll be a group of materials that overall are just more useful in general, like ABS is kind of a standard in the industry at the moment. To the point, I don't really see much point that you'd go back to like POA and whatnot, because it is for this process overall a lot better and a lot more useful. So for the most part, I think, yeah, they would stick to a standard.
We are live. Perfect. So, thank you all very much. Thank you to our speakers for a fantastic series of talks. I can only apologise for the technical issues halfway through. That's entirely my fault. So, thank you for your patience with that. I will say thank you to those who've joined us on the live stream. We're going to cut it there. For those of us in person, there are refreshments through in the Nebworth suite. I would ask that the judges are allowed to go in first to be able to get their refreshments, and then they can go ahead with their discussion of scores. If anyone wishes to use the bathroom, by the way, it's just out of that door, first door on the left, as though you're going to the stairs. You'll see the doorway there. So with that, I would say thank you all very much for your attendance. I'd say another round of applause for our speakers, and yeah, thank you all. I'll hand over to our judging panel to announce who has what they would like to announce.
Well, I think firstly, I think we'd like to comment generally on the incredibly high standard of the presentations this evening, because I think we've enjoyed a broad range of topics today, delivered by some tremendously enthusiastic, articulate, and well-informed presenters. And I think all three of us on the panel, and I'm sure everyone in the audience, really enjoyed the evening. And so I think maybe just have a round of applause for the presenters, and very well done. I think we found the deliberations very difficult simply because of the high standard. There was an interesting range of topics, and the delivery styles, you know, everyone has a different way of delivering, and you know, but the level of enthusiasm and engagement with the audience was there in all cases. So it was a pretty difficult decision, but we did reach a conclusion. Do you want to do the
runner-up first? Yeah. So the runner-up with a really engaging presentation that's past my acid test, which is always to leave me not only understanding what we've been talking about, but actually to leave me feeling a little bit cleverer for having done so as well, which is good. So so the runner-up was Thaabit Khalid. Let's go to a certificate somewhere for you.
Congratulations. Very well done.
Thank you. Yeah, well done. Brilliant.
Congratulations.
Thank you.
Just to, after, as I said, the many difficult deliberations, I am pleased to announce that the winner of this year's competition is Oliver Tatlow with his presentation, History of Stealth.
Thank you very much.
Fantastic. Thank you very much. Thank you again to our judging panel for giving up their time and their effort to support us on this. And thank you to our speakers. And thank you to you, the audience. We genuinely can't do this sort of thing without the support of everybody here. So thank you all. I've taken up a lot of your time this evening. I appreciate your patience. I apologise for the technical hitch. And I'll say thank you very much. Have a good rest of your evening.